1 because the average is always going to be around 1. So the low-pass filter here is basically weight the old value higher than the new value, so that if you're just moving back and forth and still staying around that 1 value, we'll keep preferring that 1 value, basically filtering out that movement of the up and down. It's a pretty simple example. There's way more complicated things you could do. This is not intended to be highly complex. All right, so that's basically the low-pass filter case. Let's take a look at the high-pass. So now in that case, we actually want to get rid of that thing in the middle and just look at the movement, the motion of the up and down, right? So if you stop and think about that for a second, we just figured out what the thing in the middle was with the low-pass filter. So all that's, we basically filtered out everything else. But if we start and take the whole thing again, we can basically just subtract off what we just figured out from the original, and that gives us what's left, which is what we want here. So we use the low-pass filter to find that frequency in the middle. So if we take the real frequency and subtract out the value from the low-pass filter, that pretty much leaves us with the high thing. So basically, that's going to be almost the same code we just saw, right? We're going to calculate the low-pass using that low-pass filter, and then get the current raw acceleration and subtract out the low-pass value from that, which is pretty much the high-pass filter rate. It's going to give us the remainder that we didn't already just subtract out. So anyway, that's the kind of the way that you will. It's a very basic way to separate out the low frequency and high frequency movement from your acceleration data. So a pretty good sample or example rather of low pass filtering is this bubble level app, and I've actually got that over here. So let's take a quick look at that. It's kind of hard to, we can't really do it in the sim, but I can look at my smiling face here for a second. And sorry, smiling face. So if we take a look at the bubble level, sorry, it's flipped horizontally. I can't really fix that. As we tilt it, that bubble starts moving, right? So if we do this real fast, it's not kind of going crazy. We're applying a low-pass filter, so even if I'm like shaking it around a little bit, it's still tending to stay pretty much just with the level of the device. So let's actually look at one other example here. And this one is kind of taking into account both low-pass filtering and high-pass filtering to do something a little bit more interesting. Oops, hang on. I'm shaking my device a little too much. All right. So here we've got, let's take a look at the low-pass filter, which is going to give us the general orientation of the device, right? As we move around, it's going to start moving towards that orientation. But if we then use the high-pass filter to get some high frequencies out, we can start to detect like rapid movement while still kind of aiming towards the low pass to get general orientation. All right.
You said this is using a low pass and a high pass?
Yeah, so it's using both the low pass and high pass. So the low pass filter, the low pass is passing the low frequencies, which is basically the general orientation, right? So that's when it's moving back and forth a little bit. And then the high pass filter gets us like the shaking, the really rapid movement. So that's when the pedals start flying off because you're moving the device real rapidly. So you can figure out what direction you're shaking it in and that it's happening really quickly. Oh, forgot to put the.
Is that demo app? Is it a demo app?
So the first one was a sample. I believe the bubble level sample code. This app is not. And so I have to find out what the story is because I didn't write that, and it's not a sample app. I'm not sure why it's not. I got to see if I can get permission to post it. If I can, we'll get it up on the website. But I know there's been trouble getting that particular one shown in the past. It uses actually an open source physics library to do some of the bouncing back and forth. I'm not entirely sure what the issue was, but I'll look into it and see if we can get it posted. So again, no simulator support for this either. I probably wouldn't want, again, your users like tilting their Mac Pro around trying to get the accelerometer. So yeah, you have to use a device if you want to use any of these acceleration APIs. So a couple of tips for that. Use the UI view controller stuff if you're trying to do orientations. If you just want to rotate your interface, it's a great way. It wraps all the complexity of figuring out low pass, high pass filters and orientation. A lot of time was spent making sure that the device rotates at the right time when the user actually means for it to rotate. So just use UI view controller's auto rotation and it'll take care of a lot of that for you. If you do want to use raw data, try and use some filters to extract just the parts that you care about from the acceleration, so that you can ignore the really high frequency movements if you just care about general orientation, or the opposite. And disable the accelerometer updates when you don't need them to preserve power again. Let's see what kind of time we have here. Oop, almost done, huh? All right, so that kind of leads us into the battery and power management, which we'll just kind of talk about real briefly. So again, these are pretty small devices, and as small devices, pretty small batteries, they're very low power. And what kind of, what do we mean by low power? So laptops, pretty low power, right? I mean, it's a portable device, it's running on a battery. You want it to last for a while. So kind of power is probably about 20 to 60 watts is what a laptop's using. So I don't know, order of magnitude, what do you think iPhone is going to be using? Anyone? 5 watts? All right, well, sort of, not quite, no. Think less, here we are. We're going to probably be talking like 500 milliwatts up to maybe 2.5 watts. And when we're saying 2.5 watts, we're talking like we're using the accelerometer, we're got the screen on, we got GPS updates going, we're using the device. More accurate is probably, general usage is around 500 milliwatts. So super low power. And you really want to try and stay down at that low power, the lower end of that spectrum, so that you can keep the device lasting longer, because it's a pretty small power. So there's a couple of techniques that the iPhone uses to kind of maintain the duration of these batteries. One of those is dynamic clocking. It reduces the clock speed of the CPU down to be slower when it's not under heavy load. So in the event that you're not doing a lot and don't have a lot of processing going on, try not to be doing like polling weights on things, because that's going to keep the CPU alive and active, just spinning in a loop waiting for something to happen. Try and use one of the asynchronous non-blocking callbacks so that your app can go back to the kernel and get called back later, because then we can actually put the CPU in a lower power state. We also do a lot of clock gating and power gating. So the idea here is basically blocks on chips that are not in active use will get powered down so that they're not a drain on the rest of the system. So this is kind of where you want to stop using the accelerometer in cases where you don't need acceleration data, because then we can actually power off the entire accelerometer block and it won't draw any power. Yeah, I mean, everything consumes power. The radios are consuming, some amount of power. They're actually the most expensive part. This is kind of listed in order of order of the expense. And actually, transmitting on the radios is even more expensive than receiving. The CPU and GPU are probably next on the list there, followed down by the display, the hardware modules, and then finally, well, actually that's it really, but keeping the system awake actually will keep all of these things going. So when the user presses the home button and the screen turns off and the device locks, generally what we want to do at that point is put the system to sleep. We don't want to be actively running the CPU because we're not actually trying to compute anything at that point. The user's not really trying to use their device. We want to keep minimal systems awake, just like the cell network connection so we can receive calls, but in a very low power state where we're not doing a lot of transmitting. So you really want to keep in mind that you're on one of these devices and not be running all your different devices at full power when you don't actually need them. So yeah, we got a nice battery picture there. That's what you don't want to have happen. Let's avoid that. So as I said, transmitting is the most, oh yeah, what's up?
So if your app is processing something and then the user locks the phone and you're like in the middle of doing a heavy computation, what happens to that?
So the question is, if your app is processing something and the user locks the phone, but you're in the middle of doing a heavy computation, what happens? And the answer is I should know the answer, and I do not. I think it'll keep going for, well, it'll definitely keep going for a while, but I don't know if there's a timeout period on it.
30 seconds.
I don't remember if we forcibly stop it or not. I can check in and get back to you. I don't know off the top of my head. So for the radios, transmitting is the most expensive. So the kinds of things you want to keep in mind when you're doing that are, if you're doing a lot of network requests, try and batch them up all at once. So if you know you're going to send out a request or send out 4 blocks of data, try and do it all at once rather than over some period of time. Also, if you have a choice in protocols when you're picking your network protocol, try and pick ones that are less chatty, that require less transmission. And especially ones that don't require periodic transmission. the network stack tries to shut itself down into a lower power state if it's not in use for a certain period of time. So if you've got a network protocol that requires that you check in with a server like once every 5 seconds, the network stack will never be able to go into a low power state. It's going to be just up and waiting to transmit and receive constantly.